Welcome to another video on applied electronics. So I'm continuing with solving last year's questions. So starting from question 76, I already solved the first 75 questions. So question 76, what is the main advantage of electronic measuring instrument over moving coil meters? So the here answer is going to what? A, high accuracy. A moving coil instrument, what caused the coil to move within the magnetic field? So this is a repeated question, but I think in the other one that I saw, the answer here is A, electromagnetic induction. Right? Electromagnetic. What is the purpose of controlling torque in a moving coil instrument? Here, the answer is going to be what? D. This is the same as the ones that I solved. What quantity is typically measured directly by a moving coil ammeter? So if you have a moving coil ammeter, it's going to what? Current, right? A moving coil instrument of resistance 2 ohm requires a potential difference of 80 millivolts to give a full-scale deflection. The value of shunt resistance needed to give a full-scale deflection at 25 amps is so to get the shunt resistance. We know that the current, which is going to be indicated by the moving coil ammeter, is going to be this current. So I, which is the current, is going to be equals to the current which is passing through the coil plus the what? The shunt current. Now that we've known this, so to find the shunt resistance, first let's find the shunt current. So this is just going to be equals to I minus IM. And looking at this, IM is going to be equals to, we know that what the resistance is going to the voltage across VM over what? RM. So IM here, we are going to get this to be equals to the voltage here is 80 milli over, we have 2. So this is going to give us 40 milliamps. So we get 40. Now that we have this, so you can see that I can get the what? The shunt resistance. So by taking this, I is 40, is 25 from the equation, minus 40 milli. So we have 25 minus 40 times 10 to the power minus 3. So we get 24. Again, here to be 24.96 amps. Now that we've done this, we know that shunt current is going to be equals to, meaning VM over 1 RS. So we just make RS the subject. This becomes VM over RS. VM over IS. So VM we know is already from the question is 80. So we take inverse of this times 80 times 10 to the power minus 3. So we get this to be 3.2. So the answer here is going to be D. So we get the answer to be 3.2 milliohms. Now moving forward to question 80. A moving coil instrument gives full-scale deflection of 10 milliamps when a potential of 15 millivolts is applied across it. What is the resistance if it measures current up to 100 amps? Now here again, this resistance also still is talking about shunt resistance. So the same method we use for 81 is the same method. And that method was what we know that current I, which is going to be what indicated by the moving coil instrument, is going to the current passing through the coil plus the shunt current. So based on this, you can see that we are giving the IM, which is 10 milli. So I can get the shunt current to be equals to, meaning 100 minus 10 milli. So that is going to give us much, meaning 100 minus 10 milli. So that will give us 89.99. Now that I've gotten the shunt current, I can get the shunt resistance. So the same formula, we come and make shunt resistances of the output for RS equals to VM over IS. So I have here to be here this time we have 15 milli divided by 89.99. Well, this inverse times 15 times 10 to the power minus 3. So we get 1.5. So we get 1.5 times 10 to the power minus 4 ohms. So that is just going to 0.15. So is this one A? A is B. So the answer here is B. So moving forward, you can see here again this repeated. So here is going to be integrator. Here is differentiator. But this one from there were options were given, so you just have to indicate. And here's voltage. Follower. Okay, now moving to the next question. We have a certain operational amplifier has an open loop differential voltage gain of 65,000 and a common mode gain of 0.5. So we have calculate the common mode rejection ratio in decibels. So we have the formula is what? We have voltage gain, open loop voltage gain over what? Common gain, right? The common gain ratio. Now with this formula, since we want this in what decibel, we multiply by 20 log. Okay, I'm trying to make this clear. So we now have 20 log. So with this, what do we get? I get 65,000. Okay, 20 log. 65,000 on 0.5. 20 log 65,000 on 0.5. So we get this one. The answer will be what? 102.2 decibels. Now, question 8 says the following are characteristics of an ideal operational amplifier, except. So when you talk about ideal, we have infinite voltage gain, infinite input resistance, 0 watt output impedance, infinite output resistance. So here the answer again is D. We don't have infinite output impedance. A typical operational amplifier is made up of the following types of amplifier, except. So if you have a operational amplifier, we have this amplifier circuit. We have differential amplifier, voltage amplifier, we have push-pull. So yeah, here is it's repeated past question. Question 88. That is the differential DC voltage required between the inputs to force the output of a practical operational amplifier to 0 is going to what? The input offset voltage. The operational amplifier is originally designed to perform mathematical operation of a linear analog signal. So this is also repeated from the previous year. Now we look at question 90. So you can see we have a preamble in the differential amplifier shown in figure 6. So this figure 6, we have R1, R2, R3, and then RF. So we are to find, for question 90, we are to determine the output voltage V, or if what? V1 is equals to 50 millivolts and then V2 is 15. So the formula for this differential output voltage for differential amplifier is going to the feedback resistance, then we have V2 minus V1, right? Over we have R1. This is the formula we use for this. Well, we can just look at what we have and then we just do it straightforward. So you can see here from this question, we are going to have 15, right? 15 minus V2 here is 15. So 15 minus 50. So that will give us 30 milli. So 30 milli, if you have times what? RF is what? You can see RF is 100 and then R1 is 10. So 10 over 100 will give us what? 10, right? So times 10 is going to give us this 350. So we have this as our answer. Then the next one, we have to find the output. If we have V1 being equals to V1 8 millivolts and V2 0. So here you can see the same formula. I mean, I'm going to take 0 minus 8. So that's going to give me minus 8 milli. Then times 10, we get 80 milli. So we get this one as well. Now moving to the next question, question 82. An inverter operational amplifier has the following parameters. So we have Ri 1.5, RF 2.5 kilo ohms. And what will be the output voltage when the input voltage is minus 0.8? For inverting operational amplifier, the output voltage is going to equal minus RF over Ri times Vin. So you can see here RF is 2.5 kilo ohms. So we have 2.5 kilo ohms divided by 1.5 kilo ohms. Then times minus 1. Then times, you can see here we have minus 0.5 as our Vin. So times minus 0.8. So you get 1.33. So the answer here is A. What will be the output voltage for the summing operational amplifier in figure 7? So this one is, again, this is a repeated question, right? Which we solve. I think I solved this on the previous one. Here, the formula is going to be output voltage for summing operational amplifier is going to be equals to we have our minus the feedback resistance that we have. Then we have V1 over R1 plus V2 over R2 plus V3 over R3. So this is the formula, and we can just use this formula straightforward. You can see here V1 is what? 0.5, R1 is 10. So I can just take here 0.5 and take 0.5 on 10 plus here, because they are all in kilos, so we can do this straightforward, plus 0.8 on 20 plus 1.2 on 30. So we get, when you get 0.3, and remember this is RF, and RF here is 50. So we multiply this times minus 50 rather. You can see here. So you get minus 6.5. So here we minus 6.5. And a non-inverting operation amplifier has the following parameters. We have R1 4 kilo ohms, RF 20 kilo ohms. What will be the output voltage when the input voltage is minus 0.5? So for non-inverting operational amplifier, the output voltage is going to be equal to 1 plus RF over RR, then times what? Vin. So you can see that RF is 20, so 20 kilo ohms divided by 4 kilo ohms. So you get plus 1, that will give us 6. So this one you get 6 here. Now 6 times what? Minus 0.5. So you get minus 3. So the answer here is D. Now question 85, this signal voltage applied to the inverting input appeared amplifier, but phase inverted at the output, right? So we have an operational, this is repeated past question, application of equal signal to the inputs of an operational amplifier result in 0. When you apply equal signals to the, let's say we have 0. The positive feedback is also called regenerative, right? We call it regenerative because here it's going to be added to the gain again, then as a result can increase in stability. Regenerative. Then we have question 88. A voltage follower has a closed loop gain of what? 1. We know for voltage feedback, the output voltage is close to what? The input voltage. So the voltage gain is going to be 1. Which of the following is or are true regarding signal rejected in common mode? So they have the same phase. So they have the same what? Frequency, the same amplitude. So here the answer is all of them. So this is repeated as well. The standard operational amplifier symbol has how many inputs? So the inputs, there are 2. We have inverting input and the non-inverting input. So we've come to the end of what? The solution. Have a nice day and then be well prepared for the coming examination. Bye-bye.